we're going to look at different derivative rules. So we have that limit definition of a derivative, but there are some quick tricks and different rules we can apply so that we don't have to use that limit definition every single time. So I'm going to go through them. So the derivative of a constant function is just going to be 0. So it doesn't matter what number it is, the derivative is going to be 0. So y equals -4. Well, y prime is going to be 0. Or s of t equals 45. So s prime of t is going to be 0. F of x equals 0. 0 is still a number. So if I do the derivative, f prime, it's still going to be 0. And then we have this one here. We got y equals k pi over 2, where k is just a constant. So all of that is still just a constant. So the derivative is 0. Then we have the single variable rule. So the derivative of just a single variable is going to be 1. And I'll show you with the power rule that's next why this is 1. So if f of x equals x, then f prime of x equals 1. If s of t equals t, then s prime of t is 1. If x of t is t, then x prime of t is 1. If g of u is u, then g prime of u is 1. All right, now here's the power rule. So say we have a single variable, but it has an exponent that is not 1. We can use the power rule, which is where we take the exponent and we can multiply it out front. And then we need to subtract 1 from that new exponent. Okay? So x squared, we bring the exponent down, and then we subtract 1. So we have y prime is 2x to the first power. Right? F prime, bring the 4 out, multiply, and then subtract 1 from the power. So 4x cubed. We can turn radicals into fractional exponents. Remember, it's power over root. So x to the first power, and this is the square root. So then when we do a derivative, we can take the exponent out front to multiply it, and then subtract 1 from the power. So 1/2 minus 1, I'm going to do it as 2 over 2. That's going to give me a -1/2. Or you might write it like this and turn that back into a radical. Remember, negative exponents go into the denominator. Right? We can rewrite this rational function here as g of x is x to the -1. So when we do the derivative, we can pull the exponent out as a multiplier and then subtract 1 from the power. And notice what happens here. -1 minus 1 is -2. And then it just depends on if any directions say we want only positive exponents. We can turn that back into a positive exponent and make that -1 over x squared. Same idea with this one. We can make that x to the -2 so that our derivative is -2 x to the -3, or -2 over x to the third, right? You can make this x to the -2/3 so that the derivative is -2/3. Then we'll subtract 1, so -2/3 minus 3 over 3 is -5/3. And we can go back to the single variable rule here, like say we have f of x equals x. It's really x to the first power, right? We can apply the power rule and say, hey, the derivative, we bring the 1 out front, and then 1 minus 1 is 0, right? And then anything to the 0 power is just 1. So we still can technically apply the power rule. Just it happens to be if we have a variable reach the first power, we can just make that 1. All right, now all these examples A through F for this power rule did not have a constant multiplier out front or a coefficient out front. And there will be cases where we do have them. So what can we do? We can still apply the power rule, just when we multiply by n, or that exponent out front, if there's already a number out there to begin with, we can multiply those two together. So in this case, we've got y equals 3x to the second. So y prime, we have 3 times the exponent, and then subtract 1 from the exponent. So this gives us 6x. I like this one. S of t equals negative 5t cubed. We do a derivative. We can bring out the exponent to multiply, make that a negative 15, and then we can subtract 1 from the power. So negative 15t squared. Again, we can rewrite radical as rational exponents. So 6x to the 1/2. So we do a derivative, we get 6 times 1/2, and then subtract 1 from the power. Then we can simplify. 6 times 1/2 is actually 3. So 3x to the negative 1/2. And we can turn it with a positive exponent if need be. Right, we can make this a 3x to the negative 2 to then do a derivative. So 3 times negative 2 is negative 6. And negative 2 minus 1 is negative 3. Rewrite this one. We got 4x to the negative 1/2. So my derivative will be negative 2x to the negative 3/2. And then this one, I'm going to rewrite that as negative 8 times x to the negative 4/3. So when I do a derivative, I've got negative 8 times negative 4/3, and then we'll subtract, so negative 7/3, and I'll clean those numbers up. So that is going to be 32/3 x to the negative 7/3. All right, and so far, all of these examples have been monomials, meaning there is only one term in the equation. We can do things if there's more than one term. So we have a sum and difference rule. So if we have the sum of two functions or more, we can take the derivative of each piece and add those together. And the same with the difference. So let's look at these here. And I didn't leave enough space here, so I might go in the space below the box here. But we can like separate these into its own terms and just apply the power rule here. So the derivative of x cubed is 3x squared. The derivative of negative 5x squared is negative 10x. And then we've got plus 2 and then minus 0, which we don't really need to write the minus 0, right? And notice how I just combined them with the signs that were there. Let's try another one. I said I was going to go below the box, and then I didn't end up doing that. So I've got 2/5 x to the, 2/5 times 5x to the 4th plus 4x cubed plus 6x, and then plus 0. I'll clean this first term up. Those 5's will reduce down to 1, so really I'm left with 2x to the 4th plus 4x to the 3rd plus 6x. Do some more here. I'm going to rewrite that as x to the 1/3 plus 5x to the 1/2. So when I do my derivative, I can use that power rule, make that 1/3 x to the negative 2/3 plus 5/2 x to the negative 1/2. And then I might rewrite this last term. Instead of 4 over x, I'm going to make that 4x to the negative 1. So y prime is going to be 5 times 3/2, which will be 15/2, and subtract 1 from the power. And then I've got 6 times 5/3, which will make 10x to the 2/3. And then I would say plus, because it's separated with an addition, but when I multiply 4 times negative 1, it's going to make a negative 4. So we would have plus negative 4. We don't usually have two operations like that. So instead of plus minus, I'll just put minus 4x to the negative 2. All right, I'm going to rewrite this one as 3x squared minus 4x to the negative 2 plus 2x to the 1/2. Then I'll do a derivative. So h prime of x is 6x plus 8x to the negative 3 plus x to the negative 1/2. Because 2 times 1/2 is just going to be 1. All right, I don't have a rule just yet. It'll come in a couple minutes. For a function like this, it's the quotient rule, but we haven't got there yet, so we're going to break it apart. If we have a function divided by a monomial, we might be able to separate it and simplify, right? Because if everything's divided by x, I could then make this 8x cubed divided by x plus 4x squared divided by x minus 3 over x. And then I can do some simplifying. So really that's 8x squared plus 4x and then minus 3x to the negative 1. Now I can do a derivative easier with the power rule. So I got 16x plus 4 plus 3x to the negative 2. All right, we have a product rule and a quotient rule. So product rules, if we have two functions that are multiplied together, we don't just take the derivatives of them and multiply them together. We have to do what I call lefty right plus righty left. So we take the first function. So normally to me that's the left function. And then we multiply it by the derivative of the other one. So it's left d right. But then I have to add in the right function times the derivative of the other function. So right d left. That's how I remember it. Left d right plus right d left. Or you can have it as the sum of one function times the derivative of the other plus the other times the derivative of the other, which that's a mouthful, and that's why I do left d right plus right d left. And we can potentially, you could multiply functions out. Like I could multiply this out right here and make that a 2x squared minus 8x minus x plus 4. Combine like terms. And then do power rule from there. You can. If that's a quicker way for you, you sure can. But let's apply the product rule. So the left function times the derivative of the right plus the right function times the derivative of the left. And then I can simplify from here and say, all right, 2x minus 1. And then this would be 2x, what was that, minus 8. Combine some like terms, 4x minus 9. Isn't that the same thing we'd get here? F prime would be 4x minus 9. So we get the same things. Arguably, this example might have been quicker to multiply it out, but sometimes maybe there's big functions that don't multiply out like that. Like think x and then sine of x. Nothing we can do there to make it easier. So we'd have to do product rule. So let's try it again here. So I do the left function times the derivative of the right plus the right function times the derivative of the left. And now, because I think some like terms are going to combine, I will go ahead and distribute these. So that's 4x cubed plus 12x squared minus 4x. And then this side will give me 4x cubed plus 6x squared minus 10x minus 15. And then I can combine some like terms. So 4 and 4 makes 8x cubed. Then I have 12 and 6, so that's going to make 18x squared. Negative 4 and negative 10, so negative 14x. And then the only constant is that minus 15. Okay. So let's look at the quotient rule. So as long as the denominator, the derivative is not 0, then we can apply the quotient rule. Because maybe we can't split it and simplify like the one problem I had up here, right? So let's apply the quotient rule. So this one is where I say we have low, right, d high minus high d low all over low low. That's how I remember it. So we've got low, which is x minus 5, times d high, which is the derivative of the top, minus, and I throw a big bracket over here because we want to subtract off the entire quantity of high d low. So I do a bracket for myself to know that, all right, if this simplifies out, I will have to distribute a negative. So low d high minus high d low all over low low. And now we'll just do some simplifying. So let's see, we got 6x cubed plus 8x squared minus 30x squared minus 40x. And all of this right side is multiplied by 1, so I do just have to distribute that negative. So negative 2x cubed minus 4x squared plus 7 all over. And for the time being, I won't FOIL that out. And let's combine some like terms. So we get 4x cubed plus 4x squared. Oh, I forgot about that 30. Try again. So 8 minus 30 is what? Negative 22. And then minus 4 is negative 26x squared minus 40x plus 7 all over x minus 5 squared. And I don't think if I were to try and factor out this numerator that I would have a factor of x minus 5 to cancel out. So I would leave it as it is. I don't think it gets any simpler in the form that it's in. So we're done. So let's try it again with another example. So we've got low d high minus high d low all over low low. And then we'll simplify. So 12x squared plus 4x minus 6x squared all over 3x plus 1 squared. And then that's going to leave me with, what is that, 6x squared plus 4x all over that 3x plus 1 squared. And here's where I would stop. I don't think taking a GCF out would get a 3x plus 1 factor to cancel out. But we could do GCF and say 2x. So then I'm left with 3x plus 2 over 3x plus 1 squared. But again, nothing cancels out to simplify, so I'm fine with that first one of 6x squared plus 4x over that 3x plus 1 quantity squared. Okay. So let's just do some more like mixed problems here. So y equals 5, that's a constant function. So the derivative is 0. All right, we have a power rule situation here. So 5 times 18, I don't know that off the top of my head. Okay, 90x to the 17. Applying some more power rules here. Let's see, that would be 20x to the 4th plus 1. And then 16x to the 3rd minus 5. And plus 0, but we don't need to write plus 0. 3 times 5/4 is going to give me 15/4, and then I'll subtract 1, and that'll leave me with 1/4. And then I got 5/4 times 2/3. We can either say that that's 10/12 and reduce that to 5/6, or I see that as these cancel out, and that'll leave me with 5/6 immediately. So 5/6, and then we subtract 1 from the power, so -1/3. All right, now we got 20x to the -6. I'm going to rewrite that as 3x to the -3. So we have -9x to the -4. Then we got 2/3 x to the -1/3. I'm going to rewrite that as -2x to the 1/4. So I'd have -1/2 x to the -3/4, because that -2 times 1/4 can reduce to that -1/2. All right. Eight thirds x to the third plus 5 plus 3x to the -4. And then we have -2x to the third plus 5x to the, let's see, subtract 1, so 2/3 plus 2. Right, all of those were in x. Oh, this is funny. This might be a typo because I wouldn't have written x to the first power. We normally don't write that. But we're going to do it with respect to the given variable. So since all of these equations are written explicitly, the variable is the one that's not y. So we have -15r to the 4th minus 10r. I'm going to rewrite that to be -3s to the -2 minus 4s to the -4, so that our derivative will be 6s to the -3 plus 16s, not x, s to the -5. Let me rewrite that one. Let's make that x squared plus 1. Okay? I think that sounds better. So, quotient rule here. Let's make that low times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And then we'll see if we can simplify anything further. So 5x squared plus 5. I'm going to do two things at once, and I'm going to distribute here and apply the negative. So that's 10x squared, so minus 10x squared, and that's -4x. So it's really positive 4x all over x squared plus 1 squared. Simplify just a little further. Make that a -5x squared plus 4x plus 5. I don't think anything can simplify from there, so I will leave it. I think the intention is for this to be a product rule, but I can distribute and make things a little easier. So let's make this a 5r to the 5th plus 3r squared, and then apply just the power rule. So 25r to the 4th plus 6r. All right, let's, we can do a couple things with this. You could apply quotient rule because that is the quotient of two functions there. So could do that. I see this as t plus 1 and then multiplied by t to the -1/2. And then we could distribute and make that t to the 1/2 plus t to the -1/2 and do power rules here. So 1/2 t to the negative 1/2 minus 1/2 t to the negative 3/2. That to me is a little bit quicker than doing quotient rule. So that's what I would do. And then if you do the quotient rule, you might not simplify out all the way to this exact form. So you know what? Let's do it just to see it. So let's do that. So low times derivative of the top minus top times the derivative of the bottom all over the bottom squared. So we'd get the square root of t minus, and I'll simplify this first. So we have, oh, that's supposed to be a t, not an x. So that would be t to the 1/2 plus 1/2 t to the negative 1/2 all over square root squared is going to leave me with t. And let's see what we got here. We got square root of t minus t to the 1/2 plus 1/2 t to the negative 1/2. All over t. And I think I can combine these somehow. I can make that, but then this is going to cancel out. So I think I made a mistake somewhere because I got 2 terms left over here. I see what has happened. I forgot my 1/2. That should be a 1/2. This should be a 1/2. So when I combine these like terms here, we get 1 minus 1/2, which is 1/2 t to the 1/2 plus 1/2 t to the negative 1/2 all over t. And if I simplify that further, it's going to be 1/2. And I can use exponent rules to subtract. So 1/2 minus 1 is negative 1/2. And then negative 1/2 minus 1 is negative 3/2. So we can see that it actually does simplify all the way down to the same thing. So we can use either rule there. And just for the sake of product rule practicing, let's do the product rule. So left times d right plus right times d left. And then we'll simplify. So 3 plus, it's actually be a minus, that 2. And minus 12x to the negative 3. So 1 minus 12x to the negative 3. I don't know why that doesn't seem right to me. Left, d right, plus right, d left. When you multiply, you add the exponents. You multiply, you add the exponents. Now, if I would have done the distributing, I guess we would have, because that would have been x plus 6x to the negative 2. So we'd have 1 minus, yeah, okay. I don't know why I was thinking that was crazy. So it works. Alrighty, so that is some of the derivative rules. So if you have any questions, let me know.